So far in this section, we've been talking about lines in R3. Well, we've been avoiding planes in R3. Now we're going to be talking about planes in R3. How do we get there? We start off by talking about lines in R2. So let me write down a sample equation for a line in R2. It's going to look like AX plus BY is equal to C. Maybe you call this like standard form or something like that. I don't really care what the terminology is, but this is what a line R2 looks like. A plane R3 is going to kind of have the natural generalization of the formula for a line R2. It's going to be a formula for a plane R3, namely AX plus BY plus CZ is equal to D. So constant times X plus constant times Y plus constant times Z is equal to a constant. This is going to be our plane in R3, just like constant times X plus constant times Y is equal to a constant. That's our line in R2. And to do a little bit more motivation, so the next slide is going to give you the equation, the formula for the equation of a plane in 3 dimensions. I want to talk a little bit just about the meaning of this line R2 equation here. So let's take a very simple line. So y is equal to 2x plus 1. This is about as simple of a algebra question, graph the equation of this line. Okay, so this is written in slope-intercept form. Let me write here x and y. So the intercept here is 1, its slope is 2, so I go to the right 1 unit, I go up 2 units. So, okay, so this is our line, y is equal to 2x plus 1. We're drawing a picture of this. But let me take this line. So this isn't in this kind of line here, this kind of form. Let me rearrange this. This is our usual way of writing it. But if I subtract 2x from both sides, I get negative 2x plus y is equal to 1. Now, like this imagine this form, but this is probably not your most natural way of writing it. But there's one advantage to it, which is going to be that I can rewrite this as negative 2 comma 1 dot product with x comma y is equal to 1. So negative 2 comma 1 dot xy is negative 2 times x plus 1 times y, exactly what we see right there here. So my question to you is, what does this vector negative 2, 1 have to do with this line? And here's the answer, and I think this is pretty insightful. So if we move, so we know from this stuff, our slope here is 2. So that means move to the right 1 unit, move up 2 units. Over 1, up 2. So this vector here, if I put a vector that is, moving alongside the line, this vector, this blue vector here would be 1 comma 2. Move to the right 1, up 2. But I could also think about having a line that is orthogonal. I could also think about having a line that's orthogonal, that's perpendicular. So let me put a little perpendicular sign here to our line. And this vector here, by properties of so like the slope is going to be the negative reciprocal of this slope. A vector that is orthogonal to our line here is negative 2 comma 1. And I think we've seen that before. So the idea here is that this is this negative 2 comma 1, it's the normal vector here. So it's a normal vector dotted with x comma y gives us some constant here. So there's a normal vector going on here with lines in R2. You probably never thought about this before, but it's one way to think about it. And it happens to be the way that does the right generalization to kick it up to planes in R3. Because what's going to happen here, ax plus by plus cz, if you're a little bit clever here, you can instantly see this is going to start looking like a comma b comma c dot product x, y, z on the left side of that here. And so I think I've said enough to motivate this. Let's get into our theorem. Equation of a plane here. The plane through the point, P naught, X naught, Y naught, Z naught, normal to the line, N is AI hat plus G plus B J hat plus C K hat. Here are three separate ways to write it. Vector equation, the normal vector dotted with P0, P. So P being a generic point here, X, Y, Z here is equal to 0, or A times A X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught is equal to 0. And if we simplify this down by moving the constants A X naught, B, the X naught, Y naught, Z naught to the right, we can write it in this form. And then finally, let me just kind of point out here to maybe better match what we just were talking about. We could rewrite this as, so N is A comma B comma C. This is N dot product X comma Y comma Z down here, or A, B, C dot X, Y, Z is equal to our D. So this is many different ways to write an equation of a plane. They're all equivalent to each other. Let us practice doing this in several different ways. So let's write equations for a plane through P1, negative 4, 2, 3, with normal vector 1, negative 7, 6. So let me start off with the component equation. So let me write down, so it's going to be something times x minus something plus something times y minus something plus something times z minus something is equal to 0. So something, let me put a little thing there, times x minus something plus something times y minus something plus something times z minus something is equal to 0. What are those somethings here? The outside coefficients a, b, and c, those are just coming from our normal vector. So 1, negative 7, and 6. Throwing in the inner somethings here, x naught, y naught, and z naught, those are the points in our plane that we're given here. So x naught is negative 4, y naught is 2, z naught is 3. So our equation for the plane here is going to be 1 times x minus 4, I'll write as x plus 4, minus 7 times y minus 2, plus 6 times z minus 3 is equal to 0. Yeah, so this is our equation for the plane. If you want to simplify it, we can do some arithmetic here to write it in this form. So we're going to peel off, so x plus 4 minus 7y, minus 7 times minus 2 is plus 14, plus 6z, 6 minus 3, 6 times minus 3 is negative 18, and that still is equal to 0. And by dumb luck, this all ends up equaling 0. And so we just end up with x minus 7y plus 6z is equal to 0. If this were not equal to 0, If this were not equal to 0, then we just move it to the other side right there. But let me finally point out here, I kind of ignore this vector equation here, but, you know, from P naught to P, you know, P being a generic point with coordinates x naught, y naught, z naught, so n times P naught P is equal to 0. So n was given to us in the problem as 1, -7, 6. Dot product with, so going a vector from P naught to P would have entries x minus 4, y minus 2, and z minus 3. Using that -4, 2, and 3. And so then when we expand out this dot product, we get exactly this. Okay, so we will definitely do a lot more examples of this in future videos, but this is, you know, this gives you the equation of a plane.